In today's video, we will look at limits and continuity. Let's take a look. Let's say we have this function right here. Let's call this A, and let's call this some value here, L. Now, this function is clearly undefined at f of A. However, what happens around f of A? That is, what's happening in a small neighborhood around A. Well, as we get closer and closer to A, it would appear that f of A is getting closer and closer to L. What if we now examine a function like this? Again, let's call this point A. We'll say, let's say this is L here, and let's call this down here M. Now again, f of A is undefined. But now how's the function behaving around A? Well, if we come and look only on the left-hand side, it would appear that as x is approaching A, f of x approaches M. If we now look at the right-hand side, it would appear that as x is approaching A, f of x is approaching L. If we now look at something like this, again, let's call this A. Again, f of A is undefined, but how is f of x behaving as we get closer to A? Well, it appears as x is approaching A, f of x blows up to infinity. So these give us the concept of limits. That is, how is a function behaving near a value? So let's suppose f of x is defined when x is near the number A. We will write this and that is read the limit of f of x as x approaches A if we can make the values of f of x arbitrarily close to L by restricting x to be sufficiently close to A. Right, this means that we can make f of x as close to L as we want simply by restricting our value of x to be sufficiently close to A. Now we're going to keep this idea. F of x is defined when x is near the number A. We write limit as x approaches A from the left. F of x equals L. Right, so limit as x approaches A from the left of f of x is equal to L. This is known as the left-handed limit. If we can make f of x arbitrarily close to L by taking x sufficiently close to but less than A. We write limit so limit as x approaches A from the right of f of x is equal to L. This is known as the right-hand limit. If we can make f of x arbitrarily close to L by taking x sufficiently close to but greater than A. So with these, there is an observation that can be made. The limit as x approaches A of f of x is equal to L if and only if the one-sided limits are equal to L. Now, let f be a function as defined on both sides of A. This right here, limit as x approaches A of f of x equals infinity, means f of x can be made arbitrarily large by taking x sufficiently close to A. We also have this one right here, right? Negative infinity. This means f of x can be made arbitrarily large negative by taking x sufficiently close to A. And we can form similar definitions if we're talking about one-sided limits. Now with this, we can formally define what is meant by a vertical asymptote. So if any of the following conditions are satisfied, then x equals A is a vertical asymptote for f of x. First, the right-handed limit at A is infinite, so plus or minus infinity. 2, the left-handed limit at A is infinite. And 3, the limit at A is infinite. Now, this limit as x approaches infinity of f of x equals L means that f of x becomes arbitrarily close to L as x becomes sufficiently large. And this limit as x approaches negative infinity of f of x equals L means f of x becomes arbitrarily close to L as x becomes sufficiently large negative. This allows us to formally define a horizontal asymptote if the limit as x approaches plus or minus infinity of f of x is equal to L. We say y equals L is a horizontal asymptote of f of x. So let's now look at some basic limits. Starting with the limit as x approaches A of x. So let's look at a graph. So remember, x is a line, slope 1, that passes through the origin. So what this means is if this is A, then this value is also A. Right, so no matter how we're approaching, if we're coming in from the left to A, notice that f of x is getting closer and closer to A. Same thing as we're approaching x equals A from the right-hand side. F of x is also approaching A, so it's then easy to see that this limit is simply A. If we now look at limit as x approaches A of C, for a real number C, let me not use that terminology, C is a constant. Well, if we look at the graph of a constant, Let's say this is C up here. That is a horizontal line. Now, it doesn't matter where A is, right? No matter where we are along here, right? F of x is always going to be approaching C. So again, it's easy to see that that limit is C. We are now going to introduce the limit laws. So for these, we're going to say the limit as x approaches a if f of x is equal to L, and the limit as x approaches a of g of x is equal to m. We're also going to say c is a constant. Then here are the laws. Limit as x approaches a of f of x plus or minus g of x is L plus or minus m. So the limit of a sum or difference is the sum or difference of the limits. Limit as x approaches a, c times f of x is equal to c times L. So we can pull constants, constant multiples outside of a limit. Limit as x approaches a of f of x times g of x is equal to L times m. So the limit of a product is the product of the limits. Limit as x approaches a of f of x over g of x is L over m as long as m is not equal to 0. Number 5, limit as x approaches a, f of x to the nth power is equal to L to the n, where n is any integer. And finally, number 6, the limit as x approaches a of the nth root of f of x is equal to the nth root of L, where L will have to be greater than or equal to 0 if n is even. From these limit laws, we find that if p of x is any polynomial, then the limit as x approaches a of p of x is equal to p of a. Now, if f of c yields any of the forms 0 over 0, infinity over infinity, infinity times 0, or infinity minus infinity, we say f of x has indeterminate form at x equals c. So if this occurs, we need a new way of finding the limit. Well, we can use this proposition, which states that if f of x equals g of x whenever x is not equal to a, then the limit as x approaches a of f of x is equal to the limit as x approaches a of g of x. We now will turn our attention to the idea of continuity. So again, let's look at some graphs. So let's say here we have a graph of a function. And the question is this function continuous at A? Well, from our intuitive understanding of continuity, I could not draw this graph without lifting my pencil. So this is not continuous. Right? Specifically, it's not continuous at x equals A. What about this function? So we do something like this. Well, again, this is not continuous. Again, specifically at x equals A. For the same reason, I had to lift my pencil in order to draw the entire graph. Now, what about this function? Once again, this is not continuous. And again, specifically at x equals A. Well, if we take a look at these three graphs in particular, this first graph, f of A was not even defined. The second graph, f of A was defined, but we had a jump in values. Here, f of A was defined, and we didn't have a jump in values. However, the limit was not f of A. All right, if we look at these three graphs, we can define what it means for a function to be continuous. Right? So if and only if three conditions are satisfied, one, f of A is defined, two, limit x approaches A if f of x exists, and finally that limit is f of A. A function that fails one of these three is said to be discontinuous. There are three special types of discontinuities. Let's look at graphs. So the first type is something like this. Notice here that the limit as x approaches A if f of x exists. Right? It is whatever this value here is. Let's call it L. But it does not equal f of A, which is this point up here. So this type is known as a removable discontinuity. The second type looks something like this. Now here, notice that the two one-sided limits exist. Right, here's A. But notice they are not equal. This is known as a jump discontinuity. Right? And the idea of jump discontinuities actually leads to a new idea known as one-sided continuity. Right? So f of x is continuous from the right if the limit as x approaches a from the right of f of x is f of a, which in the example I just drew, it is right-hand continuous. Right, it's continuous from the left if the limit as x approaches a from the left is equal to f of a. And a function that is both left-handed and right-handed continuous at the point A is continuous at the point A. The final type of discontinuity, or special discontinuity, is something like this. There's A. Right, this is a vertical asymptote, right? Notice that the left-handed limit is infinite, and in this case, the right-handed limit happens to be infinite. Well, this is negative infinity. This type of discontinuity is known as an infinite discontinuity. However, it doesn't have to be the case that both sides are infinite, as long as one of the sides are infinite. So, for example, this would also be an infinite discontinuity. We say that a function f of x is continuous over the open interval a to b if it is continuous at every point in the interval. It is continuous over the closed interval a to b if it is continuous over the open interval a to b, continuous from the right at a, and continuous from the left at b. And just by taking the appropriate parts, we can define what it means to be continuous over half open intervals. That is left to the viewer. So some properties of continuous functions. First, if f and g are continuous at a, so are f plus or minus g, k times f for some constant k, f times g, and f over g, as long as g of a is not equal to 0. Second property, polynomial, rational, radical, exponential, and logarithmic functions are continuous over their domain. And third has to now deal with limits. This is known as the composite function theorem. Says if f of x is continuous at L and the limit as x approaches a of g of x is equal to L, then the limit as x approaches a of f of g of x is equal to f of L. Now what this is essentially saying is that we are allowed to pull limits inside of continuous functions. We will now conclude this video with several examples. Alright, so first let's look at limit as x approaches 3, x squared minus 4x. Now, since this is a polynomial, we can simply plug in 3 for x. And we get negative 3. Let's look at limit as x approaches 2, x cubed minus 5x minus 1. Once again, this is a polynomial. We can simply plug 2 in. Eight minus 10 minus 1. Here we get negative 3. Limit as x approaches negative 1 of the square root 2x squared plus 3. Now what we're allowed to do is check negative 1. 2 times negative 1 squared is 2 plus 3 is 5. So this function is continuous at 5 at the square root. So we can just do this. And then say this is the square root of 5. Let's look at limit as x approaches 4 of 2x over 3x plus 1. Now here, this is a rational function, so we can just plug in x equals 4, as long as the denominator won't be 0. We get 8 over 12 plus 1, which is 13. Now, we're going to say that f of x is a piecewise defined function. And we want to find the limit as x approaches 2 of f of x. So to do this, what we need to do is check the one-sided limits. So let's first look at the limit as x approaches 2 from the left. Well, if we're approaching from the left, that means that x is less than 2. So we're really taking the limit of x squared plus 1. That is 4 plus 1, which is 5. If we now look at the limit as x approaches 2 from the right, that means that all the values are going to be larger than 2. So we're taking the limit of x minus 1. That is 1. Now notice that these are not equal. Therefore, the limit as x approaches 2 of f of x does not exist. Now, let's look at the limit as x approaches 3, x squared minus 3x over 2x squared minus 5x minus 3. Now, it's rational. So if we were to go ahead and plug in 3, we would get in the numerator 9 minus 9, and in the denominator 18 minus 15 minus 3 is also 0. We have 0 over 0. And recall that this is indeterminate. So what we want to do is take a look at the function we're taking the limit of. Let's go ahead and factor the numerator and denominator. So we can factor an x out of the numerator. And the denominator will factor x minus 3 and 2x plus 1. Now we can cancel out the x minus 3's, and this function is equal to x over 2x plus 1 as long as x is not 3. So this function here, this g of x, is equal to this function here, this f of x, everywhere but 3. So the limit as x approaches 3, x squared minus 3x over 2x squared minus 5x minus 3 is equal to the limit as x approaches 3 of now this x over 2x plus 1. Plug in 3, we get 3 over 7. Now let's look at limit as x approaches negative 1, square root of x plus 2 minus 1 all over x plus 1. If we plug in negative 1, we get in the numerator 1 minus 1 is 0, and the denominator we also get 0. Once again, we have indeterminate. So what we want to do is try and simplify the function. Here what we're going to do is we're going to rationalize it. Right? So we're going to multiply by the square root of x plus 2 plus 1 all over the square root of x plus 2 plus 1. Notice that the numerator will become x plus 2 minus 1, and the denominator will be left with x plus 1, and then times that square root of x plus 2 plus 1. Simplifying the numerator. Now the x plus 1's will drop out, as long as x is not negative 1, and we'll be left with 1 over the square root of x plus 2 plus 1. So then our original limit is now equal to this limit. Plugging in negative 1, we get 1/2. Let's look at this limit. Now again, if we just plug in x equals 1, you'll find we get 0 over 0. So let's go ahead and simplify this function. To do so, let's go ahead and simplify the numerator first. So we need a common denominator. What we're going to be left with is 2 minus the quantity of x plus 1 all over 2 times the quantity of x plus 1. That'll all be over x minus 1. This will then become 1 minus x all over 2 times x plus 1 times x minus 1. Now here, it looks like there's nothing else we can do. However, there is. We can factor a negative out of the numerator. And now notice, x minus 1s will cancel out, and we'll be left with negative 1 over 2 times x plus 1, as long as x is not 1. So the limit as x approaches 1 over x plus 1 minus a half all over x minus 1 is now the limit as x approaches 1 of negative 1 over 2 times x plus 1. And this is equal to negative 1/4. So let's go ahead and look at some limits at infinity. So limit as x approaches infinity, 3x minus 1 over 2x plus 5. Now the idea here is take the highest power in the denominator and divide everything by it. So we will divide everything by x. What we're left with is 3 minus 1 over x all over 2 plus 5 over x. Now these two terms will go to 0 as x goes to infinity, and so what we're left with is 3/2. And the same analysis is done if x is going to minus infinity. Let's look at this limit here. Same idea, we want to divide everything by the highest powered term in the denominator, which in this case is x cubed. So what we will have is 3 over x plus 2 over x squared all over 4 minus 5 over x squared plus 7 over x cubed. All these will go to 0. Sorry, and that one. And we're left with 0 over 4. And again, the same idea with x going to minus infinity. Let's look at this. So divide everything by that x. And that 2 over x goes to 0. Notice what's happening here is that this numerator is going to keep growing without bound. So this is positive infinity. Now, if we were taking the limit as x goes to minus infinity, we'd still do the same thing. We want to divide everything by x. Right, this 2 over x is still going to 0. But now what's happening to the numerator? It's not growing larger. It's growing larger in the negative direction. And so this would be negative infinity. Let's look at this. Again, we want to divide by the highest term in the denominator. Right now it's hard to see. So let's do this instead. Factor out an x squared. We're left with 4 plus 5 over x squared. Now we can take out a square root of x squared, and the square root of x squared is the absolute value of x. So now what we're dividing by is an absolute value of x. Since x is going to positive infinity, absolute value of x is just positive x. So we'll have 3 minus 2 over x over the square root of 4 plus 5 over x squared. This is 3 over root 4, which is 3 halves. Now I'm not going to go through all that work again. If we had negative infinity, what we have is now all the values of x are negative. So the absolute value of x becomes negative x. So we now have negative 3 plus 2 over x in the numerator. Then this is negative 3 over root 4, which is negative 3 halves. Now let's look at this. If we divide everything by e to the x, we'll be left with negative 3 over 5, right? Because again, 2 over e to the x will go to 0, 7 over e to the x will go to 0. What if we have x approaching minus infinity? Well, to see how this would work, write negative x is approaching infinity. Then we can write this as 2 plus 3 over e to the minus x over 7 minus 5 over e to the minus x. Now this is easy to see that those two terms will go to 0, and we are now left with 2/7. And we've got just one final example. We have the function f of x is equal to negative x squared plus 4, x less than or equal to 3, 4x minus 8, x greater than 3, and we want to determine if this is continuous at x equals 3. So remember, to be continuous at a point, there are 3 conditions that have to be satisfied right here. F of a must be defined, the limit has to exist at a, and that limit has to equal f of a. So let's check each of those. Is f of 3 defined? Well, if x is 3, that is less than or equal to 3, so we'd have negative 9 plus 4, which is 5. I'm sorry, negative 5. Thus, f of 3 is defined. Now, does the limit exist? Well, we need to take the one-sided limits. So limit as x approaches 3 from the left is the limit as x approaches 3 from the left of negative x squared plus 4. That is negative 5. Limit as x approaches 3 from the right will be the limit as x approaches 3 from the right of 4x minus 8. This is 12 minus 8, which is 4. Those are not equal, which implies the limit as x approaches 3 of f of x does not exist, and therefore f of x is not continuous at x equals 3. That will do it for this video. In the next video, we will begin studying the derivative.